Good afternoon. My name is Stephen Smith, and I am the IonFlux Technical Director at Fluoxetine Biosciences. I would like to thank you for taking the time today to learn about the IonFlux automated patch clamp systems. Specifically, this webinar will focus on temperature control using the Herd potassium channel as an example. Due to our unique microfluidic design, the system is superior for maintaining temperature control. First, a bit of background about Fluoxetine and the IonFlux platform. For those of you who are not familiar with Fluoxetine, we are a privately held, venture-backed company that was founded in 2005 out of technology developed at the University of California, Berkeley's Sensor and Actuator Center. The company currently has 4 products commercialized and selling globally. We've been awarded 5 NIH Small Business Research grants, including Phase 2 development grants. As well, we have been a 2-time R&D 100 award winner, winning awards for both the BioFlux and IonFlux platforms. We have 2 product lines, the BioFlux systems, which are used for studying the impact of flow and cell-cell interactions. As well, the subject of today's webinar, the IonFlux systems for automated patch clamp, which include the IonFlux 16 and IonFlux HT. Shown on this slide is a partial list of our customer base for both the BioFlux and IonFlux platforms. We know how to deliver innovative products to the marketplace, and we know how to support them, both in terms of training as well as manufacturing consumables on a large scale to meet demand. Our goal in designing the IonFlux system was to raise the bar in terms of performance for automated patch clamp, as well as lower the cost. We have made significant progress in achieving these design imperatives with the systems that we offer. For the throughput levels achieved, we have the lowest cost automated systems, both in terms of hardware costs and ongoing maintenance costs. In terms of raising the bar for performance, our microfluidic design allows for continuous flow during the experiment and exceptional fluid exchange times. With essentially only 2 moving parts and all of the liquids contained within the microfluidic plate, the instrument is extremely robust and easy to maintain. Since the electrodes and pneumatic control lines come in from the top of the plate, we are able to incorporate temperature control at the bottom of the plate, allowing for automated experiments that can be run at physiological temperature. The top of the plate, where the solutions will be loaded either manually or by a liquid dispensing robot, has a standard SBS format, a 96-well format for the IonFlux 16, or a 384-well format for the IonFlux HT. Using a standard SBS format makes it easy for the system to be integrated with standard lab robotics for plate handling and liquid dispensing tasks. Shown on the left is an example of an IonFlux plate. Bonded to the bottom of the standard SBS plate is a proprietary polymeric material containing the microfluidic channels. We refer to the collection of chambers and their channels as an experimental pattern. An IonFlux 16 plate has 8 experimental patterns, and an IonFlux HT plate would have 32 such patterns. Taking a closer look at the experimental pattern, we see that an experiment will utilize 12 wells. 2 of the wells, noted with T1 and T2, will be loaded with internal buffer. The T in this case stands for trap zone, so each pattern has 2 trap zones, an N of 2 for each experiment, if you will. There is a single in well which will contain the cells and the extracellular buffer. The connection of the in well to the 2 trap zones constitutes the main flow channel. There are then 8 wells, denoted C1 to C8, that will contain the extracellular buffer along with compounds to be assayed, although these just as easily could be solutions with different ionic compositions or other such variations on the theme. As well, one could load a pattern with different internal solutions in T1 and T2 to compare the effect of different internal components. For each pattern, there's a single outwell into which the solutions will flow. All of these solutions, including the cell suspension, would be loaded into the plate either manually or by a liquid dispensing robot prior to loading the plate into the IonFlux Reader. Once a plate has been loaded with solution, it is drawn into the IonFlux Reader, and a manifold with the recording electrodes and the pneumatic control lines is mated to the plate, shown schematically on this slide. The control of the pneumatic pressure is defined in the IonFlux control software and allows for fast control and for the compounds to be applied in any order desired. Since the fluid flow is all driven by pneumatics, there is no need for robotic liquid handling, making the reader a much simpler and easier to service device. The silver chloride electrodes are connected to the amplifiers. Since both the IonFlux 16 and the IonFlux HT are using standard SBS format plates, the only difference between the two platforms is the configuration of the manifold, thus allowing for an easy upgrade path when higher throughput is needed. We employ ensemble recording, which increases success rate and reduces variability. The pneumatic interface enables highly parallel experiments that run across the full plate at one time. Beyond the simplicity, one of the nice features of this design is that the bottom of the plate is completely accessible during the recording process. Having this access allows us to bring a heating element into contact with the bottom of the plate for performing experiments at physiological temperature. Since all of the solutions are loaded into the plate and the heating element is in contact with the bottom of the plate, all of the experimental solutions are at the same temperature, and thermal gradients are not created when switching solutions. The IonFlux systems are the only commercially available automated patch clamp systems which allow for this type of access. To calibrate the temperature control system, a plate is loaded with physiological buffers, but not with cells. In this state, the electrical measurement is a measure of the resistance of the trap zone, the open hole resistance. As the temperature is increased, the activity of the ions increases, which is manifested as a decrease in the open hole resistance. Shown on this slide is the open hole resistance measurement over time as the temperature is increased from 30 to 35 degrees Celsius and then to 40 degrees. Note that it takes about a minute for the temperature to rise, and the system is stable at the elevated temperature. A feedback loop maintains the temperature of the plate. Shown on this slide is a list of channels and cell lines that we have tested to date. This list includes a number of ligand-gated as well as voltage-gated channels. And we've also tested some primary cells with endogenous levels of ion channel expression. The pharmacology column indicates that we've recorded modulation by blockers and or positive modulators of the ion channel target with a good fit to literature values, while optimized means that we are able to obtain success rates in excess of 80% for particular systems. Additional information for a number of these channels and cell lines can be found in the form of application notes at our website. For this talk, we will be focusing on the hERG potassium channel, which has some well-characterized temperature-dependent changes in kinetic properties, as well as the pharmacology. Shown in the upper right panel is a characteristic hERG response to a change in membrane potential. From a holding potential of minus 80 millivolts, the voltage is first stepped to minus 50 millivolts, and then to plus 20 millivolts, at which point the hERG channel opens, but rapidly transitions to an inactivated state. When the membrane potential is stepped back to -50, there is a relief of inactivation, giving rise to a large tail current, which then slowly deactivates as it transitions back to the closed state. This deactivation is accelerated when the membrane potential is stepped to -120 millivolts. Note that this characteristic current is similar when run at room temperature, shown in black, or near physiological temperature, shown in red. However, the activation and deactivation processes are accelerated. In this instance, the peak tail currents have been normalized to highlight the difference in the kinetic processes. Shown in the upper left is the deactivation process from these same sweeps, highlighting the accelerated deactivation. Shown in the lower panel is the current voltage relationship for the activation process. This shift of nearly 20 millivolts in the half activation voltage has been reported by Zoe and colleagues under manual patch clamp conditions. This was reproduced by Andrew Golden and colleagues at Novartis using the IonFlux platform. The work of Golden's and colleagues is currently in press in assay and drug development technology. One of the attractive features of the hERG potassium channel as an exemplar system is that the pharmacology has been extensively studied and a broad range of compounds block the channel. Shown is a list of some well-characterized reference compounds. These compounds span a range of structures and physical properties. The octanol water partition coefficient, C log P, can be used as a surrogate measure of stickiness, which can lead to reduced observed potencies. Compounds, like terfenadine, which has a C log P of 6.5, show a large variation in literature values, likely due to this problem of compound loss to absorption. Shown in the middle column are the values obtained on the IonFlux system at room temperature. The continuous flow during the IonFlux experiment helps to ensure appropriate pharmacological characterization, even for sticky compounds. Glenn Kirsch and colleagues at Chantest have examined a range of compounds by manual patch clamp at room temperature and near physiological temperature. One of the compounds that shows a pronounced shift in the IC50 when run at physiological temperature is erythromycin. Shown on this slide is an experiment where escalating concentrations of erythromycin were tested, first at room temperature, and then again in the same run at near physiological temperature on the IonFlux. The upper panel is a plot of the peak tail current over time. After a stabilization period, escalating concentrations of erythromycin were run. Note that at room temperature, a 100 micromolar concentration of erythromycin doesn't produce any appreciable inhibition of the hERG current. And even a 1 millimolar concentration only produces a 50% inhibition. In the middle of the experiment, the heater was activated and set to 35 degrees Celsius. Note that the amplitude of the tail current increased and after several minutes stabilized. During the second challenge with erythromycin, the 100 micromolar concentration now reduces the hERG current by almost 50%. And at 1 millimolar, we see near complete inhibition. The experimental run was completed with a hammer concentration of quinidine, which produced complete block. In the lower panels are representative sweeps from the experiment. This data is in accord with the published observations of Kirsch and colleagues. Fluoxetine, another well-characterized hERG blocker, does not show a pronounced shift when run at near physiological temperature. Indeed, we see a slight reduction in potency when run at near physiological temperature. Another compound which does show a shift in potency is sotalol, and shown in the table are the IC50 values for fluoxetine, erythromycin, and sotalol when tested at room temperature and near physiological temperature, along with the values reported in the literature from manual patch clamp studies. In conclusion, due to the unique microfluidic design of the IonFlux platform, automated patch clamp experiments can be run with continuous perfusion, producing an experiment closer to the manual patch clamp situation. Since all of the experimental solutions are loaded into the plate prior to initiating the experiment, there are no thermal gradients generated during compound switching on the IonFlux. With the IonFlux 16 run at near physiological temperature, we have reproduced the key kinetic and pharmacological changes noted in the literature to the hERG potassium channel. The IonFlux systems represent the next generation in the evolution of the automated patch clamp technique. At Fluxion, we are raising the bar for performance while lowering the cost of access to this technology, with the IonFlux 16 system selling for near the price of a manual patch clamp rig. Thank you for taking the time today to learn about the IonFlux systems. If you'd like additional information, please visit our website or contact your regional distributor. Thank you.